Hi Prof, we are from group 34 and we'll be tackling the plant seedling classification task from Kaggle using our solution called Without. I'm Zhen Tian and here are the rest of my team and also their presentation order. A quick run through of the presentation agenda. First will be a formal introduction to the task and problem statement and our brief solution. Next, Brandon will be talking about the data processing techniques we have tried and the ones that we have found success with. Following that will be Ronald, who will be talking about the evaluation of pre-trained models and selection of models. Last but not least, Hengkai will elaborate on our solution and end off with a conclusion. A quick introduction to the task is to actually make clear the definition of a seedling versus a weed. Plants which are intentionally grown in fields and gardens are called cultivated plants. All other plants which grow at the wrong place or are undesirable are called weeds. A weed is therefore a plant growing in the wrong place. This applies to seedlings as well. Over here in the image, we can see that there are undesired weed in red at the bottom that the owner did not have the intention to cultivate. And they look pretty similar to the ones that the owner are trying to cultivate. Hence, this brings us to our problem statement. The seedling stage of a cultivated plant looks very similar to that of weeds. The ability to identify seedlings swiftly and accurately and to remove weed at an early growth stage is paramount in achieving healthy high crop yield and better stewardship of the environment. And our brief solution will be a highly accurate classification model to identify different types of plant in their seedling state to ensure weeds are being weeded out as soon as possible. For exploratory data analysis for images, we focus on getting statistics of the images and its properties. We can see that there are 4,750 training images versus 794 test images spanning across 12 classes. Since our goal was to actually get a very accurate classifier and a decent score in the leaderboard, we went ahead and calculated the accuracy goals to hit the top 10, 30, and 50% respectively. We can see the leaderboard score is indeed competitive. A simple blood plot also helps us identify the issue of imbalanced spread of training images over the 12 classes, which indicates the need to balance training data. Next, we plotted the 12 classes of images with their respective dimensions, and from there we could tell most of the inputs are square images with varying sizes. This will be key in determining the input dimensions of our training inputs and the scaling of images. Lastly, we also ran a visual analysis on random images of the 12 classes. We can see that most of them have similar soil-like background, and the main differentiating point is the green portion of the seedling itself. A closer inspection also helped us to spot a major challenge in the task, where two classes, namely black grass and Lucy silkband, are very similar and look alike, and this may pose problems to our classification model.
Thank you, Zhen Tian. I'll be addressing data preprocessing, which is an essential step in any machine learning task. Now that we have explored the data, we need to work on it in order to increase the quality of the data and the useful information as it directly affects the model's ability to learn. In our project, we attempted three main preprocessing methods. First, image preprocessing by masking and image sharpening. Second, balancing of the imbalanced classes with two methods, synthetic minority oversampling technique, smoke for short, and generation of class weights. Lastly, image augmentation, where we use the image data generation from the TensorFlow library. In image preprocessing, we use masking to remove the background of the image. We also improve the clarity of the image through sharpening by enhancing the fine details of the image. For masking, we first convert the image from BGR values to hue saturation values, as HSV works better for object detection. We then set parameters such that only the green portions of the image will be kept. This is done so that the main focus of the image will be the leaves and the stems. For sharpening, we first create a slightly blurred version of the original image using Gaussian smoothing. We then use the weights to smoothen the image while increasing the intensity of the edges by lowering the weights for the pixels around the edge. This will result in a sharper and a clearer image. As you can see from this graph, it shows the result of the seedling classifier with and without masking and sharpening. At the beginning, the image with masking and sharpening shows a higher accuracy than those without. However, as the number of epochs increase, the accuracy of the classifier without masking and sharpening appears to perform better. This may be due to the inaccurate masking of the images, as you can see from here below. This might result in crucial loss of information, which causes misclassification. Next, we address the problem of imbalanced classes that we have found from the exploratory data analysis. Imbalanced classification may result in a bias to the majority, which is undesirable. To address this issue, we evaluate two different methods. The first method is SMOTE. What SMOTE does is to generate synthetic data for the minority class to fix the imbalance. It does this by assigning weights based on the Euclidean distance from the nearest majority samples and also creates synthetic data using the weighted minority samples with a clustering approach. The second method is to do a weight generation based on the size of the classes. A bigger weight is assigned to the minority class, while a smaller weight is assigned to the majority class. This will penalize misclassification errors made by the minority class and thus reduce the bias due to imbalanced classes. These weights are generated using the compute class weight function from the scikit-learn library. As you can see from this figure, it would seem that SMOTE does not perform as well as the generation of weights in both the training and the validation accuracy graph. This can be explained by the synthetic dataset generated by SMOTE. Although SMOTE is very effective in handling class imbalances, it would seem that it is ill-suited for image preprocessing as synthetic images generated by SMOTE are unrealistic. Next, we have image augmentation. Image augmentation is done to increase the amount of datasets that we have. The image features such as the height, the width, the shear, the zoom, as well as the orientation are tweaked to create a slightly different version of the image as you can see here. This is done so that the model will be more robust and its ability to generalize will improve. Augmentation is done by the image data generated from the TensorFlow library. Overall, we note that image preprocessing did not improve the accuracy of the classifier. Hence, for preprocessing, we will only address the class imbalances by the generation of weights, and we will also do image augmentation at every epoch to improve the model's ability to generalize. Next, I'll hand my time over to Ronald where he'll talk about the models.
So now I'll be walking through the process of us selecting which pre-trained model we have chosen for this project. So first of all, before understanding the pre-trained models, we have to understand how transfer learning works. So transfer learning is basically reusing elements from a model that has been trained on a similar task. Typically, a neural network requires large amounts of data to accurately train a model. In this case of image classification, models have been trained by the big players in the AI industry, such as Google and Microsoft. So feeding large amounts of data and long hours of training allows the model to tune its weights and biases of each hidden unit within its layer of the neural network. This allows the convolutional layers in CNN to produce a more accurate feature maps which better extracts the features of the input images. Therefore, a better trained model would produce better accuracy results. Transfer learning utilizes these pre-trained models by reusing the network architecture and pre-calculated weights and biases of the network. A knowledge transfer is done from the pre-trained model to the new model that is required for the new task. This is done by reusing the weights of the pre-trained models and feeding in new data so that the weights are recalculated to better fit the new task. So the numerous benefits of using transfer learnings are as such. For the case of the Seedling's image classification task, 4 pre-trained models are evaluated. Those are the Inception V3 model, Efficient Net V7 model, Exception model, and the Inception ResNet V2 model. All these models are available on the QRes application API and trained on the same ImageNet dataset. The ImageNet dataset contains over 14 million labeled images and over 20,000 classes. This amount of data is generally not possible to be collected and processed by a single person. Therefore, since these pre-trained models were trained for a similar task of image classification, transfer learning can be used for the new model to classify the Seedling images. So model A is the Inception V3 model. It's made to reduce the computational power by modifying the previous Inception architecture. Various changes such as factorized convolutions, smaller convolutions, asymmetric convolutions, auxiliary convolutions, and grid size reduction were implemented to reduce the number of model parameters required. Model B is the Efficient Net B7. It is an efficient model architecture that uses a compound coefficient to uniformly scale network width, depth, and resolution in a principled way. In a normal neural network, as image size increases, number of model parameters increases by 2 to the power of n. But Efficient Net B7 reduces the increase in number of model parameters by increasing the number of layers and applying this compound coefficient. Next is the Exception model. It is an adaptation of the Inception model, and its name is derived from extreme inception. This model takes the principles of the Inception models to the extreme to further reduce the model parameters required. This is done by mainly implementing point-wise convolutions followed by the depth-wise convolutions. Next is the Inception ResNet V2. It is a combination of both Inception and ResNet models. This is done by introducing residual connections to the Inception model architectures. Residual connections or skip links are used to skip some layers within the network. This solves the problem of having deep networks, such as the vanishing gradients. So identity functions can also be learned directly from the skip links as well. Now, all 4 models were tested with the 3-fold cost validation and 10 epochs, along with all the other parameters kept constant. The validation accuracy scores are plotted in this table over here. We decided that Inception ResNet V2 is the best model to be used in the classification task, because although it doesn't have the highest accuracy, it has the least fluctuation in accuracy across the 3 folds. This could mean that the model is better suited to extract the features of the Seedling images, so it does not matter which fold the validation dataset is on. While the other models have their accuracy scores fluctuating, it could be due to the randomness of the cross-fold validation that is the cause of the large differences between the accuracy in each fold. So now I'll pass the time to Heng Kai to talk about the proposed model.
In this section, I'll be presenting on our proposed models for this project. Based on the K-cross validation result in the previous section, we chose inception ResNet v2 as our transfer learning model of choice. We have also added additional layers to help increase the performance of the model. Firstly, a global average pooling layer is added to generate one value for each feature map from the last layer of the pre-trained model. This produces a 1D array of values where each feature map contains the data of feature to extract from the image. Condensing the feature map will cause feature extraction of the images passed through the model to be processed faster. Next, a fully collected layer with 128 hidden units is added. This layer is to reinitialize a layer without pre-trained weights to have the model better adapt to the trained images that are fed through the neural network. Thirdly, a dropout layer is added to prevent the model from overfitting. Lastly, we use a softmax activation function to calculate the probability of each class label given the input data. For this model, Adam Optimizer is used as the learning algorithm, and a low learning weight of 0.00004 is used so that the initialized weights from the pre-trained model are not overwritten easily. Since this is a multi-class classification task, categorical cross-entropy loss was used. After training for 20 epochs, it can be seen that the performance for this model is decent, as the accuracy on the trained dataset was able to reach 97%, and the accuracy for the validation dataset was able to hit 90%. Plotting out the confusion matrix for the validation dataset, we can see that the model was able to accurately classify most of the seedlings correctly, but confuses blackgrass with loose-yuki band. One hypothesis for this confusion was that both blackgrass and loose-yuki band have similar features, which made it difficult for our model to extract unique features from each seedling and differentiate them. To tackle this problem, we propose a model that uses an additional binary classifier as shown in the figure on the left. The binary classifier was trained only using loose-yuki band and blackgrass images to further improve inception ResNet v2 classifier's prediction for these two seedlings. Whenever the inception ResNet v2 classifier predicts an image as either blackgrass or loose-yuki band, the image will be repredicted using the binary classifier, and if the prediction confidence for the binary classifier is above 95%, the new prediction will replace the old one. This method proved to work very well on both the training and validation dataset. From the classification report on the left, the precision and recall for blackgrass increased from 95 to 96% as compared to the model used in 4.1. However, although this model was able to achieve a 97.8 accuracy on the seedling test dataset, the precision and recall for some of the classes, such as maize and common wheat, can still be improved. To increase the accuracy of classes with low precision and recall, we propose the use of an ensemble classifier to replace the inception ResNet v2 based classifier. Ensemble learning can help improve model performance by aggregating predictions of multiple models. Ensemble learning helps to reduce the spread in average skill of a single predictive model, improves the average prediction performance over any contributing members in the ensemble, and reduces the variance component of prediction errors made by the contributing models. The benefit of ensemble learning is also demonstrated through the use of ensembles by majority of winners of machine learning competitions, such as the Netflix Prize and competitions on Kaggle. Our ensemble classifier consists of two transfer learning models, inception ResNet v2 and exception. Referring to the diagram on the left, the output of inception ResNet v2 and exception are aggregated, and similar to the model in 4.2, if the predicted label is either blackgrass or loose-yuki, the image will be passed into the binary classifier for reprediction. After plotting out the classification report for the ensemble classifier plus binary classifier on the validation dataset, we can see that the precision and recall for both maize and common wheat increased from 95 and 96% to 98% respectively, which is a 2% improvement in precision as compared to the previous model proposed. This model was also able to achieve an average of 98% precision and recall for all classes. With this model, we are able to achieve a 98.488% accuracy on the seedling classification test dataset, placing us at the top 6% on the Kaggle leaderboard. All in all, this classification problem was a daunting task as it provided us with many different challenges that had to be overcome, such as data processing, evaluation, and selection of pre-trained models, and understanding of why our models did not perform well. And when looking for inspiration in the Kaggle community on the discussion forum, it did not give us much insight, as most solutions provided there use simple transfer learning models with no novelty and only achieve accuracy result of 95%. However, the ML techniques and knowledge that were taught to us this semester, such as ensemble learning and K4 cross-validation, play a part in helping us find and build a model that eventually placed us at the top 6% of the Kaggle leaderboard. Building an ML model is also a continuous journey. We need to constantly train, test, and evaluate each model that we build. Evaluating the model allows us to better understand why this particular model did not perform well and what we can do to further improve it. Overall, this machine learning project has been a fruitful one, and we'd like to give thanks to both our professors for their knowledge. With these, we have come to the end of our project presentation. Thank you.